Now we'll look at Z transforms of some standard functions. So the first standard function we're going to consider is impulse function. So we'll find the Z transform for the impulse function and its corresponding ROC. So what is impulse function defined as? Impulse function in the case of discrete time signal, right? This is for discrete time signals. So del of n is equals to 1 for n equals to 0, 1 for n equals to 0, 0 elsewhere, right? 0 elsewhere. Only at n equals to 0 it is defined as 1, and for all other values of n it is 0. So we'll take the definition of Z transform, and in place of f of n I am substituting del of n. So del of n, now I can expand this summation. What can I write now when I expand this summation? I can substitute n values from minus infinity to plus infinity. So and so on, plus when n is equals to some minus 2 will start, right? I'll write del of minus 2 into z to the power 2 plus del of minus 1 into z to the power 1 plus del of 0 into z to the power 0 is 1 plus del of 1 z to the power minus 1, and so on. It goes up to infinity. Now we'll substitute the value of del of n. What is del of n? It is 1 when n equals to 0. That is, it is 1 when for del of 0. Del of 0 is 1. All other values of impulse function are zeros, right? All other values here, this goes to 0, this goes to 0, this and everything else goes to 0. So the Z transform is given by 1. Z transform is given by 1. That is del of n as the Z transform 1. Now we need to find the ROC of delta of n, ROC of the impulse function, Z transform of the impulse function. So how do we find the ROC of the impulse function Z transform? Now if you look at the impulse function, how is it in what kind of, we have said there are 6 types of signals, discrete type signals, right? What are they? Finite causal signal, finite non-causal signal, finite anti-causal signal, and infinite non-causal, infinite causal, and infinite anti-causal. Of those 6 types, what is del of n? Which category does del of n fall into? Now del of n is only defined at n is equals to 0, right? N is equals to 0. It is not defined for the negative values of n. So it is not anti-causal and it is not non-causal. So you can consider this to be a causal signal, or you can say it is only defined at 0 and no other values. So it is a finite value. So sorry, it's a finite signal. It's a finite signal only at n equals to 0. So what is the ROC for a finite signal? For a finite signal, the ROC is going to be the entire Z plane, right? The ROC is going to be entire Z plane. Entire Z plane. Now it is not defined for positive values of Z, it is not defined for negative values of Z, right? So we cannot actually classify this as causal signal or a non-causal signal or an anti-causal signal, right? So what we are going to do, we will look at the Z transform. So the Z transform is given by 1. So if I substitute z, any value for z from minus infinity to infinity, if I substitute any value of z, what will happen to the transform? My z transform is equals to 1. My z transform is equals to 1, which is a finite value, right? So for any value of z, whatever the value of my z is, my z transform is a finite value. So the ROC is going to be the entire z plane. The ROC is going to be entire z plane. So this is the z plane. This is the z plane. So my ROC is now the entire z plane. Right? I'll shade the entire z plane. Entire z plane is my ROC. Right? That is the z transform for delta of n. That is the impulse function. Now we'll move on to the next z transform, that is shifted impulse. What happens if my impulse is shifted? Right? What happens if my impulse is shifted? Now, shifted impulse is defined as del of n minus m. It is defined as del of n minus m. So what del of n minus m means? In place of, originally del of n is nothing but 1 when n is equals to m, and 0 when n is equals to 0. This is 0, and 0 when n is not equal to 0. This is original definition of del of n. Now del of n minus m means, in place of n I am going to substitute n minus m. Now what happens? It is 1 when n minus m equals to 0. That means n equals to m, and it is 0 when n minus m not equals to 0. That is n not equals to m. Right? This is the definition of the shifted impulse. Now in place of f of n, I have substituted del of n minus m. Now I'm going to use or now I will expand this summation. You can use either the shifting property or the sampling property directly, or you can simply expand this. Now if I expand this summation, what will I get? I'll get this and so on del of, let me say, some minus 2 into z power minus 2 or z power plus 2 del of minus 1 z power 1 plus del of 0 plus del of 0 plus del of 1 z inverse, and so on. At n is equals to m, I'll get, and n is equals to m, what will I get? At m, right? At m, z to the power minus m, and so on till infinity. It extends up to infinity. Now del of n minus m is equals to 1 when n is equals to m, right? Del of n is equals to, now this is my shifted impulse. Only at del of m it is going to be 1. So what will I have? Everything else goes to 0 except this term. So that is going to be 1 into z to the power minus m. 1 into z to the power minus m, that is z to the power m. This is one way of calculating the shifted impulse function. The other way is now this is my impulse, right? Now I'm comparing it with the standard form. N is equals to minus infinity to infinity del of n minus n naught into x of n. Now that is equals to x of n naught. This is my sampling property. This is my sampling property. We have studied this in the first unit. Properties of impulse function. This is my sampling property. Now when I compare these two summations, my n naught is equals to m and x of n is equals to z power minus n. So what is the summation on the left hand side equals to? It is equals to x of n naught. Now x of n is z power minus n, and at n is equals to n naught. N naught is equals to m. So n is equals to m. So z power minus n at n is equals to m. That is nothing but z to the power minus m. And for this, what is the ROC? How will the ROC look like? So z power minus m is my z transform. When I substitute z equals to 0, what happens when I substitute z equals to 0? Now let us consider first I'll consider z power del of n minus m and z to the power minus m, right? For this, what will be the ROC? When z equals to 0, what happens here? 1 by z to the power m, right? 1 by 0. 1 by 0 is infinity. So z equals to 0 will not be in the ROC. This cannot be in the ROC, right? When z is equals to infinity, 1 by infinity becomes 0. So it is a finite value. So z is equal to infinity can be in the ROC. And since this is a finite function, the ROC is going to be entire z plane, and at z equals to 0, the value goes to infinity. So I will exclude z equals to 0. I'll exclude z equals to 0. So that is how I'll find the ROC for del of n minus m. Now if I consider del of n plus m, the z transform is going to be z to the power m. Now if my z transform is z to the power m, now if I substitute z equals to 0, what happens? My z transform will now be equals to 0 power m, that is 0. It is a finite value. So this can be included in the ROC. Now z equals to infinity, if I substitute, my z transform will become infinity power m. It will become infinity. So I can't include z equals to infinity in the ROC. So my ROC is the entire z plane except z is equals to infinity. Except z equals to infinity. So this is how the ROC changes for a shifted impulse. For a normal impulse function, it is the entire z plane. For a shifted impulse function, based on which side the impulse function is shifted. If the impulse function is shifted towards the right side, then I can't include z equals to 0 in my ROC. If the impulse function is shifted towards the left side, then I can't include z equals to infinity in the ROC. Right? That is the z transform of shifted impulse function. Now we'll look at unit step sequence. Now let us consider the unit step signal. Unit step signal is defined as u of n. Right? This is the discrete signal, so I have considered u of n. Now what is u of n? U of n is defined only for values of n greater than 0. So my limits, which are from minus infinite to plus infinite, will now become 0 to infinity. 0 to infinity. Right? 0 to infinity. Now I have summation n equals to 0 to infinity z to the power minus n. Now we know this formula. This formula is the infinite geometric series, right? Summation n equals to 0 to infinity r power n is nothing but 1 by 1 minus r, provided mod r is less than 1. This is the condition. If this condition is satisfied, I can write this entire term as 1 by 1 minus r. So now I am assuming my mod z is less than 1, or mod z inverse, right? What do I have as more? If I compare if I compare if I compare this summation with this summation, what is r? R is nothing but z to the power minus 1, right? So if mod z is less than 1, mod z inverse is less than 1, then I can write this entire summation as 1 by 1 minus z inverse, right? So if I further simplify this, what will I have? This is 1 by z, so 1 divided by 1 minus 1 by z, that is nothing but, if I simplify, if I take LCM, I'll get z minus 1 in the denominator divided by z, that I'll take to the numerator. So my ROC for the unit step sequence is nothing but, my z transform for the unit step sequence is nothing but z by z minus 1. Z by z minus 1 is the z transform for unit step sequence. And what is the corresponding ROC? Mod z inverse is less than 1. That means 1 by mod z is less than 1. If I take mod z to the other side, I'll get mod z is greater than 1. Mod z is greater than 1. So how will my ROC now look like? My ROC will look like this. Since it's a Z transform ROC, I will have circles. I am going to have circles. So where is the circle now? Circle is at Z equals to mod Z equals to 1. This is my circle, right? Let me draw it clearly. My circle is something like this, right? This is mod Z equals to 1. Now since my ROC is greater than 1, so where will I draw my ROC? Where will I shade the region? It is exterior to the circle with radius 1. This is the circle with radius 1, and my ROC is exterior to a circle with radius 1. So this is the entire ROC for unit step sequence. This is the Z plane. This is the Z plane, right? So for a unit step sequence, if you have to categorize this unit step sequence into one of the six signal types, how will we categorize? This is my unit step sequence, right? Unit step sequence, it extends up to infinity, right? It extends up to infinity. N equals to 0, 1, 2, 3, and so on. So what kind of a signal this is? This is a infinite signal. This is an infinite signal because it extends up to infinity. Now, and it is only defined for values of n greater than or equals to 0. N greater than or equals to 0. That means it is a causal signal, infinite causal or infinite right-sided signal. So for an infinite right-sided signal, we have already said that the ROC will be exterior to a circle. It will be exterior to some circle. Here in this case, the circle has a radius of 1. In this case, the circle has a radius of 1. So my ROC is exterior of the circle to the radius, exterior of a circle of a radius 1. That is the Z transform for unit step sequence. Now, okay, this is how I'll write my final Z transform for U of n. It is Z by Z minus 1, and the ROC is mod Z greater than 1. Right? Now I'll find the Z transform for U of minus n minus 1. Now instead of f of n, I have minus of u of minus n minus 1. Now u of minus n minus 1, where is it defined? u of n is defined at n greater than or equals to 0, right? It is defined as 0 elsewhere, or instead of this I can write n less than 0. Now u of minus n minus 1 is defined as 1 for minus n minus 1 greater than or equals to 0 and minus n minus 1 less than 0. Now if I simplify this, I will get 1. I'll take n to the other side. N less than or equal to minus 1, 0 for n. If I take n to the other side, I'll get n greater than minus 1. Right? The same definition I'm going to substitute here. When is it 1? It is 1 for n less than or equal to minus 1. That means from minus infinity to minus 1, this function here is replaced by 1. And I have a negative sign here. Now what I'm going to do is I'm going to add 1 and subtract 1 here. Right? Add 1 and subtract 1. So these two terms, the first and the last terms, if I combine, I can write it as summation n equals to minus infinity to 0 z power minus n, and this one is plus 1. Now I am taking minus sign common, so it becomes minus of summation n equals to minus infinity to 0 z to the power minus n minus 1. Now this is nothing but in place of minus n, I'm going to substitute m. I have made a small substitution, right? Then I have summation m equals to 0 to infinity z to the power m. Now I can write this term as 1 by 1 minus z when my mod z, right, when this value is less than 1. That is the condition I have to follow, right? Now I have a negative 1 and I have a minus sign. Now let me simplify this. I'll simplify that here. Now what will I have? Minus of 1 minus 1 plus z divided by 1 minus z. So minus 1 and 1 cancel. Now I'll have z divided by this minus sign, I will multiply with the denominator, z by 1, right? Z divided by z minus 1. So my z transform for the u of minus n minus 1 is going to be z divided by z minus 1, z divided by z minus 1, and the ROC is mod z less than 1, and the ROC is mod z less than 1. Right? z by z minus 1 ROC mod z less than 1. So how will my ROC look like? I'll have a circle with radius 1 and my ROC is going to be mod z less than 1, that is interior of the circle of radius 1. This is my ROC, that is my ROC. Now this here is a left-sided signal. It is a left-sided signal and it is extending up to infinity, right? From the definition of what we have already found for u of minus and minus 1, it is nothing but it is an infinite signal and extends to the left side of my y-axis. That is, it's an anti-causal signal and infinite duration. Anti-causal signal of an infinite duration. If I have an anti-causal signal of infinite duration, my ROC is going to be interior of a circle. It's going to be interior of a circle. So this is my ROC. This is how I can verify if I have got the correct ROC, if I have found out the correct ROC. Right? Now we'll see Z transform of n into a power n u of n. N into a power n u of n. Now we have found out the ROC of or Z transform of a power n into u of n in the previous slides. When we have considered the infinite causal signal, right? We have found out the ROC and Z transform of a power n u of n. So what is the Z transform of a power n u of n? It is z by z minus a with the ROC as mod z is greater than a. This was the ROC we have found and this is the Z transform we have found for a power n u of n. Now I am applying differentiation property, right? Differentiation in Z domain. That property I will try to apply, right? What does differentiation property in Z domain states? It states that if my input signal x of n is multiplied with n, right? If it is multiplied with n, then my Z transform will be minus z into d by dz of x of z. It is going to be equal to minus z d by dz of x of z, and there will be no change in the ROC, right? This is the property of differentiation in Z domain. Differentiation in Z domain. So I'll apply this property to the already known Z transform pair, right? This is my x of n, this is my x of n, and this is my x of z. Now this x of n I'll multiply with n, so I'll get n into a power n u of n, and its corresponding Z transform is going to be minus z d by dz of x of z. What is x of z? Z by z minus a. So this I will simplify. So after simplifying, this is the result I have. So n into a power n u of n has a Z transform a multiplied by z divided by z minus a whole square divided by z minus a whole square. And what is the corresponding ROC? Corresponding ROC is same as the initial ROC, mod z greater than mod a. So this is why we have to remember the properties. When we learn the properties, we have to remember how the ROC changes when we apply certain property. How will the ROC change? So this is how we will apply properties of Z transform to find the Z transform of any given signal, right? This is an example for application of the same property for a different signal, right? Previously we have applied for a power n u of n, which is a right-sided signal. Now I am applying for minus a power n u of minus n minus 1. This is a left-sided signal, right? Everything else is same. I am applying the same property I'm applying the same property, differentiation in Z domain, and I'm calculating the Z transform and its corresponding ROC. Now we'll find the Z transform for cos omega naught n. Now for cos omega naught n, u of n, we'll find the Z transform. So in the definition of Z transform, instead of f of n, we'll substitute cos omega naught n u of n. Right? Then instead of u of n, what I can write? I can make the lower limit of the summation to 0, and instead of cos omega naught n, I can write e power j omega naught n plus e power minus j omega naught n divided by 2, right? Cos in terms of complex exponentials. Now I will make this into two summations, right? I'll separate the summations using linearity property of Z transform. Right? This is how I can separate it, right? I have 1 by 2 as my constant, summation n equals to 0 to infinity e power j omega naught n into z power minus n plus e power minus j omega naught n into z to the power minus n. So two different summations. So I can find the Z transform for this separately and this separately, and then I will add both of them. So now what happens? Now what I'm going to do? I can write it as like this, right? E power j omega naught into Z inverse whole power n and e power minus j omega naught Z inverse whole power. Why I'm writing like this? Because I want to write it in the form of summation n equals to 0 to infinity r power n. I want to represent it in this form. That is why I'm writing like this. Now, once I write like this, what can I replace it with? What is the formula for this? It is 1 by 1 minus r. It is 1 by 1 minus r, provided mod r is less than 1. This is the condition. So now what I'm going to do? I'm going to write this as 1 by 1 minus e power j omega naught into z inverse, right? Plus this one also I'll write as e power 1 by 1 minus e power minus j omega naught into z inverse, and I have a constant 1 by 2 outside, right? And to write like this, what is my ROC now? Say this term here, mod of this term here must be less than 1. So the ROC is going to be mod of e power j omega naught z inverse is less than 1, right? Mod of e power j omega naught is equal to 1. So mod z inverse less than 1. That means mod z is greater than 1, right? Mod z is greater than 1. This is for the first summation. Now for the second summation also we'll do the same thing. Now what happens? There will be a negative sign here. Mod of e power minus j omega naught is also equal to 1. So that is nothing but again mod z inverse is equals to 1 and mod z is greater than 1. So for both these summations, my ROC is mod z greater than 1, right? So this is my final ROC, right? Now I will simplify these terms here. So what happens if I simplify these terms? What will I get? It will look something like this. It is equals to 1 by 2. Now to simplify it, how can I write it? I will take the LCM, right? 1 minus e power j omega naught into z inverse multiplied by 1 minus e power minus j omega naught into z inverse. This is my denominator, and my numerator is going to be 1 minus e power minus j omega naught z inverse plus 1 minus e power j omega naught into z inverse. Right? Now I have 1 by 2, and in the denominator I will multiply. Right? I will multiply the denominator. So what will I get? 1 minus 1 into 1 is 1 minus e power minus j omega naught z inverse, right, minus these two terms I'll multiply, e power j omega naught z inverse, and the second this term and this term, if I multiply, I'll get plus e power j omega naught, e power minus j omega naught cancels, I'll have z to the power minus 2. This is my denominator, and in the numerator I have 2 minus these two terms, e power minus j omega naught z inverse plus e power j omega naught z inverse, right? If I take minus common, I'll have e power j omega naught z inverse plus e power minus j omega naught z inverse. So what is that? That is nothing but 2 cos omega naught, 2 cos omega naught multiplied with z inverse, right? Multiplied with z inverse. Now here in this term I'll take 2 common, right? I can take 2 common here. So what happens if I take 2 common? If I take 2 common from the numerator, I'll get 2 multiplied by 1 minus z inverse into cos omega naught, right? 2 and 2 will get cancelled. So I have finally, what do I have? I have 1 minus z inverse cos omega naught, right? Z inverse cos omega naught divided by 1 minus here, if I take z inverse common, here if I take z inverse common in the denominator, what will I have? I have e power minus j omega naught plus e power j omega naught. That is nothing but 2 cos omega naught plus z power minus 2. So this is my z transform of cos omega naught n. Now the same thing I can write in terms of z also, right? I can write in terms of z. So I'll multiply and divide by z square by z square. So what happens? If I multiply by z square, I'll get z square or z into z minus cos omega naught, right? Z into z minus cos omega naught divided by, if I multiply by z square into z to the power minus 2 is, z square into z to the power minus 2 is 1. So I'll have 1 in the denominator plus or minus 2 z inverse into z square is z. So 2z cos omega naught plus z square, right? Plus z square. So this will be my denominator. So this is going to be my z transform. So that is going to be my z transform. So cos omega naught n into u of n will now have a z transform, z multiplied by z minus cos omega naught divided by 1 minus 2z omega naught, 2z cos omega naught plus z square. This is the z transform, and the corresponding ROC is mod z greater than 1. Mod z greater than 1. Right? So this is the z transform of cos omega naught n. Cos omega naught n into u of n. So the ROC can be drawn something like this. I have a circle of radius 1. This is my real part of z, and this is my imaginary part of z, right? Real part of z and imaginary part of z. Now, since this cos omega naught n into u of n, how does it look like? It looks something like this, right? Cos omega naught n. This is the continuous time version, and now the discrete time version is going to be something like this, right? Something like this. And it extends up to infinity, right? It extends up to infinity. So it's a infinite right-sided signal. For infinite right-sided signal, my ROC is always exterior to a circle of radius a. In this case, a is equals to 1. So my ROC is exterior to the circle of radius 1. So this is my ROC. The shaded region is my ROC. So similarly, we can find the Z transform for sine omega naught n into u of n. Right? Similarly, we can find the Z transform for sine omega naught n into u of n. So here everything is the same. Instead of sine, I'm going to substitute complex exponentials e power j omega naught n minus e power minus j omega naught n divided by 2j. Right? And instead of u of n, I'm changing my limits of the summation. Now I'll find the ROCs. I'll find the ROCs, and then I'll simplify the equation I have here. I'll simplify the equation. And find my Z transform. My Z transform is Z. I can write in terms of Z inverse or Z. Both are same, right? Z inverse or Z. Both are same. Now, same way, I'm going to find the Z transform for R power n into cos omega naught n. Now, instead of R power n, we previously had 1, right? 1 R is equals to 1 we assumed, and we previously found out the value for cos omega naught n, Z transform value for cos omega naught n u of n. Now I have an extra term R. So every calculation is the same. I'll just have a term R here. I'll just have a term R, right? This term R is going to be here. So with the help of this term, with inclusion of this term only, I'll find my ROC. So my new ROC is going to be this entire term less than 1. When this entire term is less than 1, e power j omega naught goes to mod e power j omega naught becomes 1, and I have mod r z inverse is less than 1, right? Mod r z inverse is less than 1. When mod r z inverse is less than 1, that is mod r divided by mod z inverse is less than 1. So z inverse, if I take to the other side, I'll get mod z greater than mod r. Mod z greater than mod r. Right? So for both terms, I'll get the same ROC. So my final ROC is intersection of the two ROCs, that is mod z greater than r. Now I'm going to simplify this equation here. I'll simplify this equation, and I'll arrive at the final answer. So this is the final answer for Z transform of R power n cos omega naught n into u of n. Now, if I substitute R equals to 1, my left hand side becomes cos omega naught n into u of n, and my Z transform will become Z multiplied with Z minus cos omega naught divided by Z square minus 2Z cos omega naught plus 1. This is what we have found out in two slides back, right? 2 slides back, we have found the same answer, right? R equals to 1. So now we'll draw the ROC for Z transform for R power n cos omega naught n u of n. So in the ROC, for the ROC, I'll have my real part of Z and imaginary part of Z. This is my imaginary part of Z. So what is my ROC here? Mod Z is greater than mod R. So what is mod R? Mod R is nothing but a circle with radius R. So now I'll draw a circle with radius R. So let us assume this is my circle. This is my circle with radius R. Previously we drew a circle with radius 1. Now I am drawing a circle with radius R. So now my mod Z is greater than R. That means it is exterior to the circle with radius R. So this all region of the Z plane outside the circle of radius R is my ROC. So this is my ROC. This is 0 here. This is R, and exterior to the circle of radius R is my ROC. So this is how I'll draw the ROC of Z transform. Now similar way we will find the Z transform for R power n sine omega naught n into U of n, right? And here this is mod R, not mod 1. This is mod R. Mod Z greater than mod R. And the same ROC. ROC looks similar to R power n sine omega naught n U of n. So this is how we'll find the Z transforms for standard functions. Now we look at pole zero plots. Pole zero plots. Now if I have a Z transform, I can find the poles and zeros of that particular Z transform and I can plot them, right? So let us assume this is my Z transform. Now to find the zeros, what should I do? I should equate the numerator to 0. And to find the poles, I will equate the denominator to 0, right? This is to find zeros and this is to find poles, right? If I equate the numerator to 0, I will get Z equals to 0. And now if I equate the denominator to 0, I'll get Z equals to 1 by 2 and Z equals to 1 by 3. So these are my zeros, and these are my poles. So now I have to draw the poles and zeros. I have to plot them. So how am I going to plot them? So I'll take my Z plane. This is my Z plane, and this is a real part of Z. This is the real part of Z, and this is the imaginary part of Z. Now I'll draw a unit circle, right? I will draw a unit circle. I'm assuming this is my unit circle. This is 1, right? Unit circle. Now I have to plot the zeros and poles. Now where do I have a 0? I have 0 at Z equals to 0, right? How do I represent the 0? I'll draw a 0. I'll draw a circle here. This is how I represent a 0. Now to represent the poles, I have to draw a X sign, right? Where is 1 by 2? Where is 1 by 2? 1 by 2 is Z equals to 1 by 2 is somewhere here. And where is 1 by 3? 1 by 3 is somewhere here, right? So this is 1 by 2 and this is 1 by 3. So let me erase this and draw a bigger one so it will be clear. So if I consider this as my circle, if I consider this as my unit circle, then I have a 0 at Z equals to 0. I have a pole at Z is equals to 1 by 2, right? 1 by 2, 0. And I have another pole at Z equals to 1 by 3. This is 1 by 3, right? This is real part of Z and this is imaginary part of Z. So this is how I draw the poles and zeros, right? This is how I draw the poles and zeros. Now we'll take another example. H of z equals to z plus 2 by z square plus 1 by 4. For this I have to draw poles and zeros. First I'll calculate zeros. Zeros means I have to equate the numerator to 0. So z is equals to minus 2. And for poles I have to equate the denominator to 0. Z square plus 1 by 4 is 0. So what is z square? It is minus 1 by 4. Minus 1 by 4. Z square is minus 1 by 4. Now square root of minus 1 by 4 is nothing but plus or minus j 1 by 2. This is the roots of the denominator. That is nothing but my poles. Now I will draw the pole 0 plot for this h of z. So first I'll consider the unit circle. I have to take the unit circle. This is my unit circle. So this is the imaginary axis of z, imaginary part of z, and this is the real part of z. So where is my 0? My 0 is at z equals to minus 2. So this is 1, this is 1, and this is minus 1. This is minus 1. So where is minus 2? Minus 2 is, well, we can assume minus 2 to be at this point. So here I have a 0. Here I have a 0, right? So I'll draw a 0 here. I'll draw a 0 here. And where are my poles? My poles are at plus or minus j 1 by 2. That means the real part is 0 and the imaginary part is plus or minus j 1 by 2. This point here is nothing but j1 and this point is minus j1. So where is plus j1 by 2? It is somewhere over here. So I will draw a pole here and the other pole is at minus j1 by 2. Right? This is j1 by 2 and this is minus j1 by 2. So I have two poles and a 0. So this is how I can plot the poles and zeros. Similarly, now here I am given a I am given a system equation. If I am given a system equation, so how will I find the pole 0 plot? To find the poles and zeros, we have to find the transfer function, right? We'll find the transfer function. So I'll apply Z transform on both sides. So when I apply the Z transform on both sides, to find the what can I say? Yes, when I'm given a system equation, the difference equation for a system, then I am going to apply Z transform assuming 0 initial conditions. I'll apply the Z transform assuming 0 initial conditions and then I'll find the transfer function. I'll find the corresponding transfer function. From this transfer function, I can find the poles and zeros. The point we have to remember here is to find the transfer function of a system, I should assume 0 initial conditions. Now from this transfer function, I can find the poles and zeros. So my zeros are at z equals to negative 0.4 plus or minus j 0.8 and my poles are at z is equals to plus or minus j 0.7. So here I will draw these poles and zeros in this graph itself, right? So let me draw the So this is my Z plane. My 0 is at negative 0.4. Where is negative 0.4? This is 0 and this is minus 1. So I can assume my negative 0.4 somewhere over here. And plus or minus j.8. j.8 is somewhere over here. So here I have 1 0 and the other 0 is at negative 0.4 minus j.8. So these are my two zeros, right? This is j.8 and this is minus j.8. Now where are my poles? My pole is at 0 plus or minus j.7. Where is 0 plus or minus j.7? On the imaginary axis, somewhere right here. These are my two poles, j.7 and minus j.7. So this is how I can mark the poles and zeros if I'm given the transfer function or if I'm given the system difference equation. So if I'm given the transfer function, directly I can find the poles and zeros. But if I'm given the system difference equation, I have to find the transfer function. So to find the transfer function, I apply the Z transform and assume initial conditions to be 0. Only then I can find the transfer function. I should assume initial conditions to be 0, right? So then I can find the poles and zeros and plot them. So this is how we'll plot poles and zeros. The same procedure can be followed for Laplace transform also to find the poles and zeros. There we'll have the real part of S here and imaginary part of S here, and we'll not have any circles, we'll have strips. We'll not have any circles, right? That is the difference between Z transform and Laplace transform. Now these are the standard Z transform pairs that we have derived. We have derived all of these different Z transform pairs, right? Then we'll move on to inverse Z transforms.